Hi, my name is Clement Wong, and I'll be your student teacher for today. Today's subject is all about thermodynamics. You might be questioning yourself saying, what is thermodynamics? How does it play a role in our world? Why should I care about it? When you break down the word thermodynamics, you see thermo and dynamics. When you think about thermo, you think about heat and energy. When you think about dynamics, you think about the physical processes. When you think about it, heat and energy have played a huge role in our world. Going all the way back to the prehistoric times, thermodynamics have been applied even during the caveman time. They used fire as a heating source. As time has passed, we always try to apply the concept of heat in our own lives. Experimenting with different ways to heat up your own house, experimenting with ways to attain heat, and use heat in ways that we thought were not possible back then. Nowadays, thermodynamics is everywhere in the modern day world, such as using the refrigerator, or boiling water, or even heating your house. All these concepts relate to heat. How do you define thermodynamics? Thermodynamics is defined to be the sub-area of physical science that stresses about the importances of heat and with its relation to other forms of energy and work. So when you think about thermodynamics, you're going to think about heat transfer, or you're going to think about the amount of energy it takes to heat up this metal, or you're going to think about anything that has to relate with heat and energy. But before we start off with anything, we gotta know the difference between heat and temperature. Is it difference? But isn't the reason because my house is so warm is because of the heater? What difference can there possibly be? But let's observe through this mini cartoon.
Temperature versus heat. Here's a bucket of hot water at 50 degrees Celsius. And here's a cup of freshly boiled water at 100 degrees Celsius. In which of these two containers are the water molecules moving faster? The bucket or the cup? That's right, because the degree of hotness of the water in the cup is much higher than the degree of hotness of the water in the bucket. And the hotter something is, the faster its molecules move. Would you say, therefore, that there's more hotness in the cup than in the bucket? In that case, if the water in your swimming pool is just a bit too cold for you, you'd be better off emptying the cup full of boiling water into it, rather than the bucket full of water at the lower temperature, wouldn't you? Or would you? You don't seem so sure. Let's do an experiment to find out. Suppose you had two identical swimming pools, one yellow and one blue. And suppose that the water in both of them was just a bit too cold for you. When you pour the cup of boiling water into the yellow pool, does the water feel any warmer? You can hardly feel any difference at all, can you? Now pour the bucket full of 50-degree water into the blue pool. How does that feel? Quite a bit warmer? Aha! So even though the water in the cup was considerably hotter than the water in the bucket, the 50-degree bucket water is much better at heating up swimming pools than the 100-degree cup water. Why is this? Well, let's look at the facts. The bucket obviously contains many, many more water molecules than the cup does. The temperature of the average molecule in the bucket is 50 degrees, and the temperature of the average molecule in the cup is 100 degrees. Now let's substitute something else for the molecules. Imagine that instead of molecules, the cup were filled with $100 bills, and the bucket with $50 bills. Which would you rather have? Each individual bill in the cup is worth much more than each individual bill in the bucket. But the total amount of money in the bucket is much greater than the total amount of money in the cup. It's the same with hotness. The degree of hotness, like the value of the dollar bills, is higher in the cup. But the quantity of hotness, like the quantity of dollar bills, is greater in the bucket. We've already seen that the word for degree of hotness is temperature. Now it's time to introduce the other word for quantity of hotness, which is heat. The water in the cup has got a high temperature, but very little heat. And the water in the bucket has got a much lower temperature, but a great deal of heat. Now you know why buckets of 50-degree water are better at heating up swimming pools than cups of boiling water. On the other hand, if you're looking for somewhere to dunk your tea bag...
So whenever you picture solids, liquids, and gas, you gotta picture about particles moving within the object. Like the video mentioned, heat is all about quantity. How can you define heat? Heat is the energy caused from the moving particles. So if more particles are moving, that means that more heat is created. Since the large bucket contains more moving particles than the small cup, more heat is generated in the bucket than the cup. On the other hand, temperature, however, is the measure of the average energy caused from the moving particles. Temperature, though, is not affected by the quantity. You can have a huge object that is at the temperature of 100 degrees Celsius, and you can have this very small object that is also at the same temperature of 100 degrees Celsius. The big object, though, would have a lot of moving particles in it, thus creating more heat than the little object. But now we gotta think about how something loses its heat. Unless an object is within a closed system, the object will lose its heat to its environment. You can visualize this with a cup of hot tea, for example. If you want to cool a cup of hot tea, you're going to let it settle in an open environment. That way, the tea actually loses its energy to the environment. But is energy really lost within an open system? Why would it lose its heat? I'll give you a minute to think about these questions. The answer to the first question would be no. Energy is not lost within an open system. Why? Because energy cannot be destroyed. The second law of thermodynamics says heat always transfers from something hot to something cold. Let's visualize this law using ice. Now if I were to leave an ice cube at a warm environment, what will eventually happen is that the ice cube will eventually melt. Heat, in a way, is being transferred from something hot, the warm atmosphere, to something cold, the ice cube. Because the ice cube is gaining heat, it melts. This is the same situation when you put ice into your drinks. Since the drink is warmer than the ice, the drink actually gradually gives heat to the ice, thus making it melt. This introduces two new terms, endothermic and exothermic. When you break down the word endothermic, you see endo, which means gaining, and thermic, which means heat. Endothermic means that something is gaining heat. On the other hand, exothermic means that an object is releasing heat. So if I were to apply these two terms to something like adding ice to my tea, I can say that the tea is releasing heat to the ice while the ice is gaining heat from the tea. In this case, the ice will be endothermic and the tea will be exothermic.